The topic of synchronous machine continues, and let's look at this example. What we have is a 208 volts 45 kVA machine, but the critical thing is it is a delta connected synchronous machine which has a synchronous reactance, and this is X of S and negligible, so Ra is equals to 0 when we make the per phase equivalent. So it has also explained some friction and windage losses are 1.5 kilowatts, core losses are 1 kilowatt, and the shaft is supplying a 15 horsepower load. This is the pull load, and the motor's power factor is 0.8 leading. So the first task that is assigned to us is we have to sketch the phasor diagram of this motor and find the values of IA, that is the armature current, IL, which is the line current, and EA, which is the armature in voltage or the voltage induced on the windings. So let's first look at the machine. This is our machine, and here we have the rotor. So the important thing to know is this, that again its terminal output, there are 3 terminals that are coming from here, and there is power that is being supplied is called P input, and this P input goes through certain losses and is converted into P output. Also the current that is traveling into the machine is the line current, and the voltage between these 2 terminals is known as the terminal voltage, or we can say that this is the line voltage for the machine. Now inside the machine, the winding can be of Y nature, and it can also be of delta nature, and then there becomes a difference in how we interpret these values. For Y connected, if there is a line voltage, then the line voltage is actually between point A and B, so we had to convert this into phasor voltage to make V terminal for per phase equivalent circuit. But if it is a delta connected machine, then the voltage between these 2 terminals A and B will actually be the terminal voltage of the per phase equivalent circuit, and the per phase equivalent circuit which I am talking about is this here. Ra is 0, so this is the Vt I am this is the per phase equivalent value I am talking about. So for delta connected this becomes as Vt, but for so in this case it is a 208 volts. So the terminal voltage for our machine is 208 volts, and it is also the voltage for per phase equivalent circuit. Now let's look at what about the current. When we are talking about the current for our machine in Y connected, the phase current is actually also the line current for Y connected. But when we look into delta machine, so the line current is not the phase current. We must know this thing. So for the armature current that we have to find out, we have to convert the line current to its per phase equivalent. That's the difference between a Y connected machine and a delta connected machine. Therefore, for our given example, we are considering a delta case, and in this case, to calculate the armature current, we have to divide the line current by under root 3, so we can calculate the armature current for our machine. The terminal for per phase equivalent circuit and the terminal voltage for the per phase equivalent circuit will remain the same. Now let's see how can we find out the line current for the machine. What's the line current that is entering into the machine? This we can find out if we know what is the input power of the machine. So let's see, can we find out the input power? No, the question says that it has given us the output power, that is P out, and it has also given us certain losses that includes the mechanical losses of friction and windage and the core losses. So if you know the power flow diagram, from the power flow diagram we know that P mechanical and we have P electrical input, and there is a point first the P input is here, sorry. So there are electrical losses, then the power is converted, then there are mechanical losses and core losses, and then we find the P output for the machine. So in this case, the electrical losses, we don't have any electrical losses because armature resistance, the resistance that exists here is 0 ohms. So all the losses are of those given. So if we are able to calculate all the losses, if we know all the losses, we will be able to calculate P input. So let's look at this. So P input is actually equals to P out plus P mechanical loss plus P core and plus P electrical losses. So can we find these losses? Let's try to find out. P output, yes we can, it is 15 horsepower. As output is being taken and we need to convert this into watts. So P output is equals to 15 horsepower into 1 horsepower we know is equals to 746 watts equals to 0.746 kilowatts. So if you multiply this with just to make the units, I have to make it in kilowatts to avoid very large numbers, I have made this. So the P out is actually 11.19 kilowatts. Now let's look at the mechanical losses. They have given us the mechanical losses are 1.5 kilowatt. What about the core losses? They have also given us, it is 1 kilowatt. And we have no electrical losses as RA, armature resistance, is negligible and 0. So when we add all of these values, we will get P in. When we add all these values, the P in will be equals to 13.69 kilowatts. Now it is 13.69 kilowatts, and now if we know the input power, we can calculate the line current by the formula for a three-phase power, real power into the machine is equals to Pn is equals to under root 3 Vt IL cos of theta. Now P in we have calculated, Vt we know. Do we know cos theta? Yes, and the motor's power factor is 0.8 leading. So the value of cos is 0.8, and so by calculating this we can find out IL is equals to 47.5 amperes. Now this is the line current that is being input into the machine. But is this line current same as the current that we find in per phase equivalent? No, because we have delta connected. So we have to convert this to armature current, and the armature current, as I have previously told you, under root 3. So the armature current would become 27.4 amps. Also the power factor is the power factor for the machine is 0.8 leading, so the angle would become cos inverse of this, and the angle will be we will have the angle of 36.87 and it is positive as the current is leading. So finally the final value of Ia will become 27.4 amperes with angle 36.87. This is the current. So what was the question? Find Ia, IL and EA. So how can we find EA? EA we can find from this per phase equivalent. We know that the basic from the KVL formula, we know EA equals to VT minus JIA X of S. So VT we know is 208 volts with angle 0. Then we have X of S. The value of X of S we know is 2.5 ohms. Here it is given. Here it is 2.5 ohms. So so the current first we shall write what's the current value? 27.4 angle 36.87 with 2.5 angle 90 degrees. And by solving this, finally the value of EA that we will get is 255 with angle minus 12.4 degrees. Now if we need to draw the phasor for this, if we have to, and so to draw the phasor for this diagram, if this is what we call our VT, that is 208 volts, and we have a current that is here, and this is our IA. So what will happen is, so applying the KVL, VT with minus of the current, and this will become be minus, and then it will be shifted, and this will be actually JIA axis, and this part, and so this will be our value of EA, and this is the power angle, and the power angle for this case is minus 12.4 degrees, and as this is negative, it is purely acting as a motor action. Okay, so in this way we have calculated this. The next part of the problem states, it is actually B and C are same, that now if a part of a single question, that now if the load is doubled on the motor from 15 horsepower to 30 horsepower, sketch the behavior and also find IA, IL and EA. Again, IA is the per phase equivalent current in armature current moving into the machine. IL is into the per phase equivalent circuit of the machine. IL is the line current moving into the machine, and EA is the internally generated voltage for per phase equivalent. So how can we calculate this? So the question, very important, you need to know is that for the synchronous motors, what they have done is they have increased the load. So by increasing the load, can the internally generated voltage EA be changed? Its value is not dependent on the load. Its value is dependent on the excitation current IF. So the amplitude of EA will not change, yet the power angle will change, which will determine how much power is being drawn, because therefore the mechanical power output, as it has increased, the input electrical power will also increase, so the line current will also increase. So these steps we will see, and as I'll solve, the things will get clear. So let's see, for the new case, for part B and C, for the new case, Let's leave for the B and C. If we see that the as the shaft, here is our motor, and here it has increased the power, so the input power to the machine must also increase, as we calculated previously. In that case, output power has increased from 15 to 30. So that's how we will calculate, and this will become 24.88 kilowatts. Previously it was 11.19, and here it is 24.88. The mechanical losses and other losses remain the same. Now for the machine, for the synchronous machine with a certain per phase equivalent circuit, here this is the circuit, this is the IA. We know that the power that is being transferred in case of motor from VT to EA is actually has this equation or the formula, that is for 3 phase. This is 3 VT EA over X of S sine of delta. This is actually the power that will be transferred. So in our case, let's look at this. We have calculated this power. Here is this power. Does the V terminal change? This will not change. Will the EA change after changing the load? No, it will not change, because you have not changed IF. IF is constant, so EA will remain constant. X has changed? No, it is same. So can we calculate delta 2? The only thing that will change here, for this was the case for part A, and for the only thing that will change will be this delta. So if we solve this equation, the value of delta 2 would become, and here delta 2 becomes 23 degrees. Now as delta 2 has become 23 degrees, then we can calculate our current IA from here. This is EA, from the same strategy as we have done previously. EA equals to VT minus IA JXS, so the same formula. So IA is actually equals to VT minus EA over JXSS. VT is again 208 volts, 0 degrees, and EA is 255 with what angle? What is the angle of EA? Delta is actually this is the angle. If this is V2 and this is EA, so this angle, that is the power angle, is actually the angle of EA. So here it will be 23 degrees and divided by 2.5 with angle 90 degrees, is J22.5. So by solving this, what we will get? We will get a value of IA that is equals to 41.2 with angle 15 degrees. So this is actually our armature current. This is this current flowing into this. But is it the same current that is flowing into the machine? For Y machine, this is the same. But here we have delta machine. And in this case, this is not the current. We have to convert this into our line current. So the line current's value will be under root 3 IA, and this will become 71.4 amperes. IL equals to 71.4 amperes, and I have not done the angle shifting. Also, if you want to find the power factor, the power factor is actually the angle between current IA and voltage VT. So our theta is actually equals to minus 15 degrees, and cos of theta is cos of theta will be 0.966, in this case 0.966, and the current is actually leading, the angle is positive, so the power factor is positive. And this is how we can solve this. Lastly, I will just make the phasor diagram for case 2 with red. I will use the red. So what will happen is the terminal voltage remains the same, but what has happened is our IA dash, our current has changed, the input current to the machine, and due to this changed, our IAJXS, this part that we have, this thing, this loss, we can see this, it's like this, and the value of EA will remain same. This should be no. So here is our E A dash, and here is our delta 2. The value of EA remained same, and the current actually changed, and for in this way this graph was made. I hope it helps. Thank you. Assalamu alaikum.